In this video, we're going to be going through some practice problems from Wiley Plus relating to capacitors, capacitance, as well as dielectrics. So in this first question, we are asked to find the capacitance of the system. So this is a more unusual type of capacitor because we're working with tools here, but by definition, it is a capacitor because we have two conducting objects that are separated by a certain distance with the same charge on each with an opposite sign that has a potential difference between them. So for our first part, it wants the capacitance of the system. We know capacitance to be equal to our charge and over our potential difference. So we're given both of those things. So let's do 97 times 10 to the negative 12 coulombs. And this is over our 19. And this is equal to, so that's 97 divided by 19 times 10 to the negative 12. And we are answering units of picofarads, so we can just drop that. And in this case, it doesn't matter which charge we use. I would recommend using the positive one, but in any case, our capacitance is going to be a magnitude value. Picofarads is for our whole system. And if you remembered in the previous video, I mentioned that capacitance is consistent if the distance, our potential difference, is the same and no dielectric is inserted. So because of that, our capacitance value for B remains the same. And then for C, we can answer based on this principle. So if we want to find the new potential difference between them, right, so we can isolate for our potential difference. This is equal to our charge over our capacitance. And our new charge is 170 picocoulombs over our 5.105 picofarads. Right, since they're both to pico, then we can just use our numbers as is. And this becomes 33.298 volts is our new potential difference. Right, so for a system, as long as there's no dielectric, sorry, this statement then becomes false. If there's no dielectric, then our capacitance value stays the same. Okay, so now to answer the second question, we have two different capacitors which are in parallel, and each are charged with 88 volts with opposite polarity as shown. So what is the potential difference between points A and B once these two switches are closed? And what is now the charge on capacitor 1 and 2? Okay, so we want the total of our system first. So when these switches are closed, then our charge gets to be distributed here, and our charge will flow there. Okay, so let's first find the equivalent capacitance. So when we close both switches, then it becomes a full circuit. So we know our adding rules for when they're in parallel is just taking our C1 plus our C2 capacitance. And this would be equal to, so that's 1.5 plus 2.6 microfarads, which is equal to 4.1 microfarads. Okay, and if we were to calculate it just for each one, so if I were just to isolate C1 and then C2, we can find the amount of charge in each one after they've been dissipated. So C1 is equal to, so then that makes our Q equal to C1 times our V, potential difference. So then our Q is equal to C1, which is 1.5 microfarads times 88. That's 1.5 times 10 to the negative 6 times 88. And this becomes 1.32 times 10 to the negative 4 coulombs. And now let's just do it for our C2. So this becomes 2.6 times 10 to the negative 6 farads times 88. And this is equal to 2.288 times 10 to the negative 4 coulombs. So now we're going to calculate the net charge that we have. So our net charge is 2.28 plus 1.32 times 10 to the negative 4 coulombs, and this is equal to 3.608 times 10 to the negative 4. So then, if we use the equation C equals Q over V, and we find our net V, which is equal to Q net over our C equivalent, this will give us 608. Nope, 608. Let's try again. 608 times 10 to the negative 4 coulombs over 1.3, nope, over 4.1 times 10 to the negative 6. This gives us, so divided by 4.1,